Welcome everyone. Welcome to the second session on linear regression. In last session, we covered the basic concept of linear regression and we just came across the equation y is equal to mx plus c. We had a introduction to simple linear regression. We built a linear regression model in Excel. Then we imported a data file. The file which we are using is income expense data.csv. The file can be downloaded once you log in, and in the complementary section the file is available. This is the file that we are working on. We'll continue with this file and build our linear regression model, and today we'll try to understand the concept of R squared. So let's get started with R squared. What is R squared? When you are building a model, how good is your regression model? How good your regression equation is fitting on the data? To measure that, we have a model performance measure called R squared. You already know, in a linear regression, you predict, the regression equation predicts a value, and that value we compare with the actual value, and the difference between the predicted value and the actual value is called error. And the linear regression model, which makes use of ordinary least square technique, tries to minimize the sum of squared error. Remember, once again, it tries to minimize sum of squared error. It does not try to minimize sum of error, because error can have positive and negative values. So you actually take a square term and you try to minimize the sum of the squared term. Now, before I get into R squared formula and what is R squared, let's just have a practical, straightforward discussion. Assume you have got data of 50 households or 500 households. You have got data of households. The income information and the expense information of the household is everything available. And you quickly, in Excel, compute what is the arithmetic average, what is the mean expense of the household. Some household is spending 50,000 rupees per month. Some households are spending only 5,000 rupees per month. The average comes out to be rupees 18,818. Now you are asked a question. What is the monthly expense of household X? That X is unknown. That which is that household? I'm not giving you any information. Where is this household X located? Is it in uptown, or is it in some very poor location of the city? I'm not telling you what is the income of that household. No information provided. Only that you know is, when you have this 500 household data, you computed an average expense. The number came out 18,818. And now randomly I ask you, hey, can you tell me what would be the expense of a household X? In absence of any data, any information about that household, our best guess estimate is the mean estimate, because that household can be having very high income and very lavishly they might be living, or they might be living in a very shabby condition. We don't know. So in absence of any information, our best guess estimate is always the mean or the median statistics. In this case, because mean is given to you, we will go with the mean statistics. Now, if I give you an information that the income of the household X, for which you have to estimate the expense, the income of that household is rupees 10,000. Obviously, the moment I give you the income information, logically, we know if a family is earning rupees 10,000 rupees per month, in that case, they would try to ensure they live within their means. So they will try to ensure their monthly expense, their monthly budget does not exceed rupees 10,000. So the estimate in this case will be a number which will be definitely below the mean of the overall data, which is 18,818. If I tell you that the monthly income of the household is rupees 50,000, obviously your estimate of the monthly expense will be a number which will be above the mean 18,818. This is very logical. Now, only thing what we are doing is, in a linear regression, when income and expense information both is given, we regress the expense with respect to income, build a equation. Now, once we have a linear regression equation for any income information, we can predict what is the likely expense of the household. How good is the mathematical quantification of this linear regression equation? How accurate is our equation? If I have to measure in some way, in that case, I require a model performance measure, and that model performance measure, which one of that which we use in linear regression, is called R squared. With this background of what is R squared, let us now get into technical definitions of R squared, the concept and the calculations. R squared. R squared is a statistical measure that represents the proportion of variance in the dependent variable as explained by the independent variable in regression. This is a very technical definition, but the concept I have already explained through the example. R square is a measure which tries to tell us how much we are able to explain our dependent phenomena. In this case, the dependent phenomena is expense. How much accurately we are able to explain expense based on the independent. Independent here is income. How good income is able to predict the expense. A quantification of this is R squared. We are making use of lots of technical terms, proportion of variance, how well the model is able to explain what percentage of variance of the dependent is explained. All of that will get clarified once we get into the calculation of R squared. So you will have to just hold on for a while. R squared, there's a other name. It is called coefficient of determination. The coefficient of determination is very simple in an English language. It's a measure of how much we are able to determine the target phenomena, and that's what is R squared. Are we able to determine 80%? Are we able to determine 70%? How accurately we are able to determine? That is R squared. So obviously, when I say 80%, 90%, it has to have a value which ranges between 0 to 1. It cannot exceed 100%, right? So the value of R squared ranges from 0 to 1. When you are building a linear regression model, whether your model is good, bad, ugly, it depends on R squared value. Higher the value, better is your model. And when we build a linear regression, we try to aim to have the model R squared 0.8 or above. At least we should be able to explain 80% of the phenomena, right? So 0.8 or above for a regression model is considered to be a good regression model. With this background, we now get into the calculation of R squared. There is a formula, all of this thing, technical stuff is given here. Okay. So let's first jump into Jupyter Notebook, build an equation, get into Excel, and we'll get back to this screen to understand the R squared calculation. Okay, I just get into my Jupyter Notebook. Okay, this is not where Jupyter is. Sorry, this is where my, this is where my Jupyter Notebook is. Yeah. Okay, let me get into full screen. It's, yeah, 125%, F11. Okay. Step 1, we import some basic libraries. Shift enter. Then I change my working directory. This is my directory where my data file is there. So I'm changing my directory, and then using pandas.read CSV, I'll read the file. Shift enter. My file has been read. We have already seen that whenever we build a regression, we should first visually see. I'm not getting into those things now. Correlation is there. Note down the correlation 0.64. Let me just run the code in sequence. Shift enter, then shift enter. This is 0.64. Remember this number. We'll come back to this number later. And I am now running the regression, building the model, and I want to see the model equation. So summary of the model. Now in this model, we require this intercept and we require this beta coefficient. We'll take these two numbers, 6319.1018, copy. Let's get to our Excel. Yeah, here I have opened the income expense data.csv. You can see I already made a copy of it because we are going to work on it. I don't require these C, D, E, F, G columns. The other columns which have data, I require only the first two columns because we are building a simple linear regression. So I just hide them. I don't require them. Okay, somewhere here I'll make a note of intercept. Yeah, the number which we copied, let me just paste it. 619.1018. Let me show it to the 4 decimal places. This is the number we copied. And the beta was 0.3008. Yeah, 0.3008. What it means is the equation is expense is equal to intercept plus, that is intercept is 619. So let me just put 619 rounded off plus 0.3008 times income. This is the equation of monthly household expense with income. If this is the equation, I can compute, that is predict the expense. Given income is available, I can predict that, and the predicted value is always denoted by y cap or y hat. So let me write y hat, and predicted value will be 6319. Let's make it constant, F4 plus 0.3008 multiplied by income. So if I know the income of a household is 5,000, the equation is estimating that this household should have an expense of 7,823. The actual expense is 8,000. The prediction is very close to the actual expense. Yeah. So all of you watching the video, try these steps, reach till here. In case you have missed anything, pause, go back and come till here, because from here on, there will be lots of calculation to compute the R squared. Okay, here in this equation, I should have this as $O $2. So let me just press F4. It's become constant. We can drag and fill, double click, it will fill. So automatically the equation is now applied on each and every row. So if someone is having a income of 6,000 rupees, we are estimating the expense will be 8,123. Let us just quickly calculate. And here, let me also, before that, let's just put convention. This is our independent variable. So I'll just say X. This is my dependent variable. So let me just say Y. Okay. Now I have to calculate what is the average expense of the household. So that is called Y bar equal to, and I can take the Excel formula, average. So average is 18,818. In case I don't know income, if this information is not available, any household, if I have to estimate the expense, in absence of any information, we always rely on the average. So in that case, for any household, we will have to predict the expense of the household as 18,818. This household has 5,000 rupees as income, but this information that the income is 5,000 is not available. I end up estimating expenses 18,818. This household has got 24,000 as income. I don't know have this information. I end up estimating 18,818. This household has got 60,000 as income. I don't know this information. I end up predicting 18,818. So in absence of information, we always rely on the mean. So if we rely on mean in absence of information, our error would have been y minus y bar. Okay, so what would have been the error in each of these cases? This is y, this is minus, this is the bar. I'll make it constant, F4. So for each of the household, our estimate would be way off this much. Somewhere it would be negative and somewhere it would be positive. Sum total of this will be 0, because anything that you take as a difference with respect to the mean, in that case it has to be 0. So this is my error. Because of the information, we are able to make more accurate estimation. So what is my model error? The error which my model is leaving behind is y is actual value minus y hat. So what is the error? This is 8,000 minus 7,823, because that is the value predicted for the first household having income 5,000 using the information which is income. So my error is 176. You can see this is way off, 10,818, way off, and this is very close. The error is only a small fraction, 176 rupees. And we can just double click, autofill all of this. This information, y minus y bar and y minus y hat, for each and every row, we can represent visually. Now I'm going to show the visual representation in our blog. And this is where I come back to the blog. Let me just zoom in. F11. Let me increase the zoom. Yeah. Okay. So here, let us just imagine one particular data point from the data. So we are taking a particular record having income here. We are taking a particular record having income of 60,000. Now for this income, let's consider this particular household. There is one household which is at bottom here, but I'm not considering this one. I'm considering the top one. Sorry. Yeah, let's start once again. This one, and we are considering this particular household. Okay, we have this particular household. If we don't have a model, this purple line y bar is my mean estimate. So my error is y minus y bar. And here what I've done is I'm showing it in a squared terms. Okay, but y minus y bar is the error without model. Because of the model, this y cap, y hat, which is the regression line of best fit, is giving us an estimate that the expense of this household should be somewhere here, where I put a dot. Because of my estimate y cap, the error which is left behind is y minus y cap, or y minus y hat. This is the error which is still left. Visually you can see for the household A, for this particular household A, earlier my error y minus y bar was too big. Now because of the model, the error which is in yellow color is less. How much error we have reduced? The amount of error we have reduced is y cap minus y bar. This is the error which we have reduced. Just try to sink in this information. I'll erase all of these color lines. When we build a model, the error y minus y bar is the error which is, if we compare the data with respect to the mean. When we build a regression, we predict, and because of a prediction, we are more accurate in our prediction. As such, the error reduces. So remember, in regression, we minimize sum of squared error. We don't minimize sum of error. That's why here in the plot, in the image, all of the term has been shown with the squared terms. Let's just quickly see terminologies. each and every terminology. Let's get into those. Actual value, which is our dependent value variable, in this case expense, we denote it by y. The symbol y is used to denote the actual value of the dependent variable. Independent variable is denoted by x. In this case, it is income. The mean is shown by y bar, the purple line in the above plot. Y cap or y hat, it is the estimated value based on the model, that is represented by line of best fit, shown red color in the plot. Y minus y cap is error. Y is the actual value, y cap is the model predicted value, that is error. Error is the difference between actual and predicted. Error is also called as residual. Y minus y cap the whole square is called squared error. If I calculate y minus y cap, here I have shown y minus y cap the whole square for one data point A, but here we'll be actually calculating y minus y cap for this data point also, we'll be calculating for this also, we'll be calculating for this also, for this also, and then taking a sum of all of these values. So when we do a summation of all of these values, it becomes summation of y minus y cap the whole square, and that is called as sum of squared error. So that is represented here, sum of squared errors. Other terminology is residual sum of squares. Despite we building a model, we are not completely able to eliminate the error, and that's why sum of squared error is left. However, there is certain amount of reduction in error which is shown by the green color. How much is the reduction? Reduction is y cap minus y bar the whole square. If I take a summation across all the data points, that is called as sum of squared regression. It is the amount of error which has been reduced because of the model. If this entire model was not there, we would have predicted each and every observation to be equal to mean. In that case, we do y minus y bar the whole squared. When we do calculation with respect to mean, it is called as sum of squared total. So these are terminologies, and this is the pictorial representation. Now each and everything has to be done calculated in Excel. So we come to Excel. So here first y minus y bar, we square it. So y minus y bar the whole squared, this multiply by the same number and double click. Summation of all of these values. Summation of all of these values is called sum of squared total. So let's just type that, sum of squared total, it is equal to sum this is the value. This number, don't bother about this number. This number by itself does not have any meaning. So don't bother about what is this big number in front of us. Ignore it. It is called sum of squared total. Y minus y hat is error, but we don't minimize sum of error, we minimize sum of squared error. So I need to compute y minus y hat the whole square. So let's just do that. Y minus y hat the whole squared. This is equal to this number multiply this number itself. Double click, autofill. Once again, we do summation. So this is the sum. Once again, we have got some big number in front of us. So let me just Control X, Control V, and here let me write it SSE. And oh, sorry, Control, yeah. So this is merge sum of squared error. This is also called as residual sum of squares. Why? Despite building the model, we have not been able to eliminate the error completely. This much amount of error is still left behind. That is residual. So square of this is called residual square, and that is residual sum of squares. So the other terminology, residual sum of squares. Okay. So this is what we have. I can write here for more clarity, without model, this would be my total error. And here I can say because of model, this is my reduced error or residual sum of error, square error. Right? This is not total error. This is something which is left behind despite building a model. Obviously, there is a error reduction. So how much is the error reduction? I'm using the term error reduction. How much is the error reduction? When we say error reduction, it means how much is the squared error reduction. But in a normal English, while talking, we'll always say how much is the error reduction, like this. But it is squared error reduction. Okay. So the error reduction is this minus this. This much is my error reduction. So how much percentage I have reduced? Express in percentage form. If I express it in percentage form, this number divided by this number, it is 0.421. Okay. And this is my R squared. This 0.421 is my R squared. If we go to our linear regression and just compare R squared, 0.421 is the number. So we have just calculated the R squared, or rather than saying how much is the error reduction here, I'll rephrase this statement now. How much is the explained component. Now we'll come to this very shortly, but for now, quickly try to understand this much and do the calculation at your end in Excel, and then we'll see what is this explained variance, unexplained variance, and the significance of R squared. Okay, I hope all of you have been able to complete till this point. We in the Excel, sorry. All of you have been able to reach till here. Now I come back to my blog. Yeah. Now let us just remember the variance formula. What is variance formula? Variance formula is y minus y bar the whole squared divided by n, the whole squared. Yeah. This is a formula for variance. When I do the sum of squared total and simply divide it by n, actually it becomes variance. And if I just don't divide by n, we call it sum of squared total. So here I can say this purple bar which I have, which is sum of squared total, I can call it total variance. This is what I can call. This is total variance. Okay. Because of my regression equation, this green part is the amount of error which I am able to reduce. And when I take this green component across all the data point and I do sum of squared, basically that is, this here R is regression. SSR, sum of squared regression. Because of the regression, I am able to explain certain component of the total variance. So we call this explained variance. EXP, explained variance. And despite building my regression, the yellow part is the error which was left. And when I take this square of error across all data points, when I take the error, sum of squared error across all data points, I can call that as unexplained variance. So total variance has got two components. One is called explained variance. The other is called unexplained variance. How much variance I am able to explain as percentage of the total variance is my R squared. Just imagine all of these numbers you divided by n. This becomes total variance. This becomes my unexplained variance. This becomes my explained variance. So I'm now explaining the terminologies in a different way. Earlier I was using error term, squared error, but now I am converting them in a more explainable, business intuitive form. Total variance. Total variance is broken down into two components, explained variance and unexplained variance. Our objective of model is to explain the dependent phenomena using the independent parameters. More you are able to explain the dependent phenomena using independent, better is the model, right? And what percentage of the total variance you are able to explain is called R squared. So coming back to the Excel, I can now start writing here. If this is the number, I'll just remove all of these things now so that you don't get confused. So first is this formula. Once again, let's go up. Y minus y bar the whole square. The moment I divide it by n, it would become a formula of variance. So here, this is my summation. If I divide this summation by 50, which is number of observations, this would become my total variance. This is the component which is sum of squared error. And if this sum of squared error, just like we have divided the above number by 50, because 50 is the number of observation, if I divide this also, I can say this is my unexplained, because this is the error which is still there. So I can call this unexplained variance. Now, explained variance is equal to total variance minus unexplained variance. We can express the equation like this. So I can do this as a difference of this minus this. And if this is how I do it, I can take a percentage of this with respect to this, and it will be explained component of the total variance. So in a business way, if I have to explain the relation between income and expense, I can say 42% of the variance in expense is explained by the model, and here the model is only a single variable model, that is having only income as an independent variable. So I can say has been explained by the income. What does this mean? See, when we have a dependent variable, we are trying to predict why some household are spending more, why some household are spending less. When we are trying to predict that, we are trying to find factors by which I can give reasons why someone is spending more and why someone is spending less. And one of the factor is income. So when I take into consideration the income, I am able to increase my accuracy of prediction. However, my accuracy of prediction is not completely 100%. I am only able to explain 42%. There is a 58% still unexplained. That 58% can be because of many reasons. For example, there is a household, coming back to this image, there is a household which is at 60,000 income level. Someone is spending 50,000 and the other person is just spending 10,000. Probably in this household where there is 60,000 income, the one which is spending 50,000 may have 10 members in the family, whereas the one which is just spending 10,000 may have only 2 members in the family. What it means is, definitely income helps you explain the expense of the household, but expense of a household is not completely dependent on income. There are other factors like family size, the location where they are staying, whether they are in an urban location or a rural location, their lifestyle, their age groups, and so forth. That element is still unexplained. Income in this case is able to explain only 42%. 58 is unexplained, which means there are more parameters. If we can bring them into our model, I can better explain why someone is spending higher and why someone is spending lower. So this is the concept of R squared, in sum and substance, R squared measures how good is your model. R squared tells you what percentage of the total variance is explained. As you can see in the formula, R squared is explained variance divided by total variance, and interpretation of R squared in our case is 42.1 percentage of the variance in the dependent phenomena, that is expense in our case, is explained by the independent variable, that is income. How to compute R squared in R using the calculation, or how to calculate R squared in Python? I can use all of these steps and calculate. So let me just show now the calculation. I am sure by now you would realize that calculating all of this is less important than understanding the concept. So here, R squared calculation in Python, just for knowledge sake, I'm capturing the monthly expense as a Y variable. I'm capturing the monthly income as a X variable. Y bar I'm computing. I am using linear model, the model which we created. Using a predict function for each observation of X, I'm predicting the Y. I capture it as Y hat. Sum of squared total, sum of squared error, sum of squared regression. R squared is equal to sum of squared regression divided by total. Control enter, and I get the value 0.421. So I can do R squared. With this, we have understood the very important concept of R squared. And because our model is only able to explain 42%, it is very much clear we need to bring in more factors in our model. As I bring more factors, what I am doing is I am getting into a multiple linear regression. What we built so far was a simple linear regression. In a simple linear regression, we have only one independent variable. When we have more than one independent variable, we call it multiple linear regression. So quickly we'll get into multiple linear regression. In the meantime, just try calculating the R squared in Python also. This will help you develop your Python skills, programming skills. Okay, with this we complete the simple linear regression and the R squared concept. We now get into the next concept, multiple linear regression, and with multiple linear regression we'll see adjusted R squared, multicollinearity, and more. This also reminds me, I had in between said that kindly note down a very important number, which is 0.64. I have not touched upon this. What is this 0.64? This 0.64 is correlation. Correlation is represented by Greek symbol rho, which is in English, when we pronounce it as rho, and it's in Greek. I cannot write the symbol because we cannot keep writing that symbol easily. We typically represent correlation by symbol R. Okay, correlation is represented by symbol R. Income, expense, correlation is 0.64. Okay, let's come back once into our Excel, and this is my data which is available here also in Excel. This is X and Y, these two columns. Let's just quickly run core function, corral array 1. Array 1 is my income, and then array 2 is my expense. Definitely the correlation will come same that we saw earlier, and we use the term R. Okay, if we use the term R, what will be square of this R? Square of this R, that's 2. 0.421. 0.421. 0.421. These two numbers are matching. So basically, R squared is total variance, which is explained component of the total variance, and that if you do a square root, if I do a square root of this in a simple linear regression, if I do square root of R squared term, it gives me correlation between the independent and the dependent variable. Okay, I've completed this part also. Now I can move on to my next blog, which is multiple linear regression and adjusted R squared. Okay. Now, why do we require multiple linear regression? The reason why we require a multiple linear regression is we already saw with a simple linear regression, we were only able to explain 42% of the variance in expense. 58% of variance in expense is still unexplained. The reason why different families have got different expense level is despite having same income, probably different families have different expense despite having same income. Can be their family size is big or small. They may be staying in an urban location versus a rural location. They may have a much more flamboyant lifestyle versus they may be having a conservative lifestyle. If all of these factors can again be captured in an equation, which means I have to go from one variable to more than one variable. I go from a simple linear regression to a multiple linear regression, and that's the need of multiple linear regression, where we have more explanatory variable, we have more than one explanatory variable in our model, and it will help us improve the model performance. Okay, with that, let's quickly jump into multiple linear regression. We have to do importing, and once again let's quickly go through what data is available. We have used income and expense so far. Expense is my dependent variable. We used income as an independent variable. These are additional parameters available. How many family members are there in the household, whether the family is staying in an EMI or rented apartment, what is the annual income, what is the qualification of the highest qualified member in the family, how many earning members are there in the family. These are additional information. Can we use this additional information to build a better model is what we have to see. Hypothesis: whenever you build a regression, any modeling, you should start with hypothesis. Definitely my first hypothesis was expense is dependent on income. Null hypothesis: expense is not dependent on income. Alternate: expense is dependent. Now, if I have to frame more hypothesis, a family which is of a smaller size, their expense will be less, versus a family which is of a larger size, their income should be more, their expense should be more. So number of family members has an impact on expense. Alternate hypothesis. What will be null? Null hypothesis will be expense of a family is not dependent on how many family members are there. It is logical that expense is dependent on number of family members, but still when we frame hypothesis, it's a hypothesis. It is a general wisdom. So with a general wisdom, don't say that hypothesis does not have any meaning, but that's the concepts. Again, touching upon the hypothesis concept in linear regression. In linear regression, the hypothesis concept is null hypothesis is dependent variable is not having any impact, is not influenced anyway by independent variables, which means the beta coefficient of all independent variable is 0. Alternate hypothesis is there is at least one independent variable where beta coefficient is not 0. So you start with hypothesis framing. Many hypotheses may be very obvious. Second element, you always see the visuals between independent and the dependent variable. When we built simple linear regression, we made a scatter plot. Now here there are many variables. When there are many variables in one go, we can make the plot in Python using a pair plot function. So rather than writing for each variable, I can make a pair plot, and in a one syntax, I can have the graph. Now it is very important that you relate the plots. You should, whenever you're making a plot, don't take it as an exercise of running code. Executing code is not the objective. When we are executing the code, the objective is to interpret the output. Now, how do you read the pair plot? The way to read the pair plots is, here you have variable. So here my expense variable is there. So in all of these four graphs, this axis y is represented by expense variable. Okay, because the variable name is given here like this. So in all of these four charts, the y-axis is the expense. What is the x-axis in all of these charts? The x-axis on all of these charts is, labels of that is given below. Let me just slightly scroll. Yeah. The labels here, what is the x-axis? The label of that variable is shown here. Here it is expense. Now because expense versus expense, there is no point having a scatter plot. So it is giving you a distribution. The next one is income. So here my x is income. So this plot is a plot between income, which I represent as I, and expense. Here it is expense, the next plot. And what is the variable? It is family members. So here it is family size. I represent by fly. First thing is understanding the XY axis. Once you have understood the XY axis, you have to focus on each chart. Let me focus here. When I focus on this chart, I can see that as my number of family members are increasing, the dots are going on the upper side, which is expenses increasing. So visually, my hypothesis is proven. Bigger family size will have more expense. Now the next one, EMI or rent. So here, EMI and rent. What I can see in this graph, there is some concentration of dots. Here, there is a concentration of dots. And this concentration is because there are many families which are staying in their owned apartment. They are not staying in an apartment where they are still paying the EMI or rent, which is their expense is 0. So this is the distribution, and the rest of the data point is for those who have got EMI. So which means there's some, the trend is not very clear. And if the trend is not very clear, I need to scroll down and see what is the distribution of this variable. Okay, I see this variable does not have a normal distribution. You can see there is a huge skew. Good amount of data point is having 0 expense, 0 EMI or 0 rent, and then there is a small flattening like this, which means the point I have to note down in my memory is this variable is skewed, whereas other variables you see is more normal distributed. If they are not completely normal, but they are more fairly distributed. They don't have a huge concentration of values at certain data value point. Okay. This kind of interpretation when you are making the charts is very critical. Why this specific thing will become important, we'll see later on when we see importance of variable transformations in building linear regression. But the point is checking the trends. There's a positive correlation. there is a positive correlation. What is the trend at a broad level? Capturing that is a very important skill as a data analyst. Okay, so don't focus only on executing codes. Put some time interpreting the charts. Having interpreted the charts, you make some inferences. I've given certain inferences which I've given here. We then get into model development. Okay, so let's just get into our Jupyter notebook. So here we completed till here. We now get into this R squared. This is the SNS. SNS is Seaborn, the pair plot. I just run it. Control enter. So the plot is ready. I already explained it. In that plot there were only 4 variables. Here I have taken all the variables. I've taken earning members and EMI, annual income. So I've taken some 6 variables. So all of that has been taken here. Okay. You can also check correlations, or you can create a heat map. Okay. So here I'm just checking correlation between income and annual income. Obviously, monthly income, annual income, there are 2 independent variables. They have got very high correlation, or I can create a heat map of correlation between all the variables. And the correlation between all variables, the more the density of red or the more the density of blue, more density of red, higher positive correlation, more the density of blue, higher negative correlation. So here I can see very dark red, 0.97. The 0.97 is a high correlation between monthly household income and annual household income, which is obvious, but these are important things that we'll have to see. We'll cover that later. So now we get into multiple linear regression. So first thing is we do some basic visualizations and basic correlation between our independent dependent variables. Between independent variables also we need to check all of that. And one of the important thing is there are 2 variables which have got very high correlation, that is monthly income and annual income. How will it impact our model? We'll see later on. Okay, coming to multiple linear regression. How do we write multiple linear? This is my dependent variable, tilde. Just write independent variable plus the next independent variable plus independent variable. You keep writing like this. So this is the way we give the formula in this function, OLS function, which we are using for building our linear regression. And having given that, we call fit. Fit is to fit the regression between your dependent variable and the independent. And then we do summary. Control enter. Just by adding one more variable, my R squared has improved from 0.42 to 0.57, which means I am now able to explain 57% of the variance. Why different families have got different expense level, I am able to explain using income and their family size to an extent of 57%. Can I further increase this? Probably yes. If I add EMI, what is the EMI being paid by them? Whether if there's someone is staying on a rented apartment, definitely because of the rent, expense has to increase. And this slash, note down this slash because my equation is running on multiple lines. That's why I put this slash here. Okay. Control enter. Now if I fit with 3 variables, my R squared has gone up to 0.698. That is almost 70%. I am able to explain 70% of the target phenomena dependent variable. 70% of the variance in expense is explained by the model which has income, family members, EMI as our variable. Can I increase this further? Probably yes. I've got more variables. By adding more variables, probably I can improve this. Okay. For now, my R squared is 0.698. Now, let us also focus. What is this another statistics? Adjusted R squared given just below it. There's something R squared. They've given one more statistic, adjusted R squared. What is this adjusted R squared? The point is, when we build a multiple linear regression model, we use adjusted R square as a model performance measure and not R square. Why? We'll shortly understand why we use adjusted R square. In the meantime, quickly execute this piece of code and get the output, and then we'll get into further explanation of adjusted R squared. So far we have built our multiple linear regression, and I hope all of you have executed these codes. I'll just scroll up once so that you can, in case you want to run step by step. This is a plot. I pause here. This is correlation, heat map, and then this part of the code, I'm adding only one variable. By adding only one variable, we see there is an increase in R square. By adding one more variable, we see there is a further increase in R square. From 0.42 R squared, we have reached 0.698. That is almost 70%. And we have adjusted R square. What is this adjusted R squared? Why adjusted R square is seen? We'll see all of these in our upcoming session. Till then, I take your leave. Thank you. Bye bye. We'll focus on adjusted R square in the next session. Thank you.